Hey, good morning or afternoon. I'm going to try to give you some quick notes on section 10.1, which is about the fundamental counting principle and also permutations. We're going to start with a tree diagram, which takes a lot of time, so don't worry, you won't have to do too many. So in many real-life problems, you want to count the number of ways to perform a task. One way to do this is using a tree diagram. So let's pretend that you are getting a new car, and you can buy me one. But when you're ordering your new car, you decide to get a new SUV called the Tracker. The Tracker can be two-wheel drive, four-wheel drive, or all-wheel drive. And yes, there is a difference. Additionally, you have the option of ordering the Tracker as a hybrid or not a hybrid, as well as choosing one of 4 stylish colors for your Tracker, including red, yellow, green, or black. Let's make a tree diagram and count the number of different trackers that can be assembled. Well, first we have the fact that you're getting a tracker. The first choice you have is the type of drive it is. And we have 3 different options. So that tracker can be two-wheel drive, it could be four-wheel drive, or it could be all-wheel drive. The next option you have is if it's hybrid or not hybrid. I'm going to be lazy and put H and not H. And that's a possibility if you get the two-wheel drive, the four-wheel drive, or the all-wheel drive. The next option you have is one of the colors, red, yellow, green, or black. Well, off of this guy, I could have red, yellow, green, or black. Off of this guy, I could have, that's an R, red, yellow, green, or black. Off of this guy, so you can see that this is pretty much happening for all of these options. And so like this guy right here represents a green hybrid four-wheel drive tracker. This represents a red, not hybrid, all-wheel drive tracker. So each of these is going to be a different possibility. And if you were to count these up, you can see that you would have 24 different trackers that were possible. So that's how you can use a tree diagram to find the number of ways. However, that's kind of a pain in the butt. So instead, let's talk about the fundamental counting principle. The fundamental counting principle says that if one event can occur in m ways and another in n ways, then the number of ways that both events occur is m times n. You just multiply the number of possibilities together. It can be extended to 3 or more events. For example, if 3 events can occur in m, n, and p ways, then the number of ways that all 3 can occur is m times n times p. Let's do that for the example with the tracker above. Notice that we had different drive types. And how many different drive types did we have? 3. Then we have the hybrid option. And we basically had 2 choices there, hybrid or not hybrid. And then we have the color option. And how many choices do we have there? 4. So then we could multiply those 3 options together, 3 times 2 times 4, to get 24. And so there are 24 options. Way faster than that tree diagram, don't you think? So sometimes we'll have these license plate problems. Suppose the standard configuration for Texas license plate is one letter followed by 2 digits followed by 3 letters. First of all, let's talk about letters. How many different letters are possible? When it talks about letters, notice that there are 26 options, A through Z. I also want to point out that when it's talking about digits, a lot of people think that there are only 9 options for digits, but they're forgetting about 0. So for digits, there are 10 options, 0 through 9. Okay? So when it says how many different license plates are possible if letters and digits can be repeated, well, we have 1 letter, and then it says 2 digits and 3 letters. So how many options do we have for that first letter? 26. For the next digit, 10. For the next digit, we still have 10 because they can be repeated. For the letters, 26 options, 26, and 26. And then we could just multiply those values together. Just punch that in your calculator, and we end up with 45,697,600 different options that we have. Then it's asking about how many different plates are possible if the letters and digits cannot be repeated. Well, that means that if we use one letter, we can't reuse it over again. We still have the same idea of a letter, a digit, and 3 letters. And this time for the first letter, we have 26 options. But when we get to the second letter, we don't have 26 options anymore. We've used one of them, so now we only have 25 left. Then for the next letter, we've used 2 of them, so we only have 24 left. And then for the next letter, 23. Going for the digits, notice we have 10 digits to choose from at first. And then once we've used one, we have 9 digits. We would multiply all of these together, and then if we put that in our calculator, we have 32,292,000. So let's look at the U-tries. We'll do these together real quick. At a blood drive, blood can be labeled one of 4 types, one of 2 Rh factors, and one of 2 genders. So how many different ways can blood be labeled? Well, we have different things. We have the types, we have the Rh, and we have the genders. How many different types did we have? Looks like we had 4. Rh, we had 2. Gender, we had 2. We multiply these together. We get that we have 16 different ways. So if you made a tree diagram, how many different final branches would you have? Well, in the tracker problem, our answer was 24, and we had 24 branches. So it would follow that we would have 16 branches if we spent our life making a tree diagram for this problem. Let's look at 2. Banks use the numbers 0 through 9 to generate 4-digit PIN numbers to protect customer ATM accounts. How many different codes are possible if digits can be repeated? Well, we have 1, 2, 3, 4 possibilities. And if they can be repeated, we have 10 choices for the first digit, 10 choices for the second, 10 for the third, and 10 for the fourth, which means we would have 10,000 different possible codes. But what if digits cannot be repeated? We still have 4 options, but we have 10 digits to choose from first. Then we've used one. We can't use it again, so we only have 9. Now we've used 2 of them, so we only have 8 left. Now we've used 3, we only have 7. And if we multiply those together, now we're down to only 5,040 options for that code. Okay? So that's the fundamental counting principle in a sense. I want to talk to you about a factorial. This symbol, which is an exclamation point, is the factorial symbol. And 3 factorial is not read as like 3, like you're all excited. It's read as 3 factorial. I should write out that word, shouldn't I? So it's read as 3 factorial. In general, n factorial, you can read it on your sheet, n factorial is defined where n is a positive integer as follows. If you see n factorial, that means that you take that number, you multiply it by the number less than that, so like n minus 1. You multiply it by the number less than that, n minus 2. And then we would keep multiplying all the way down until we get to 1. We wouldn't want to keep going to 0 because then 0 would always be the answer, okay? So if we were to evaluate 6 factorial, let's just talk about what that means. That means that we'll start with 6 times 5 times 4 times 3 times 2, all the way down to 1. And if we multiply all of that together, we find that that's going to be 720. I want to show you where there's a factorial button in your calculator. In your calculator, if you go to Math, there's that Math button, and then you arrow over to PRB. Notice that number 4 is your factorial. So what we could do is, instead of typing in 6 times 5 times 4 times 3 times 2 times 1, we could take 6, hit Math, over to PRB, hit number 4, and in our calculator, if we press Enter, it tells us that that's the answer, 720. So we can very easily then evaluate 9 factorial. Notice that gives us 362,880. And 0 factorial might be a little weird for us because we can't do anything less than 0, like to get to 1, because 0 is already less than 1. So let's see what the calculator tells us if we do 0 factorial. We get 1. And that's just a definition that's used for other, when we do permutations and combinations, that formula. But that's what the factorial button is. And we use factorial in this thing called permutations. Let's back up here. A permutation is an ordering of objects. The number of permutations of R objects taken from a group of n distinct objects is noted by NPR. So n is like a little, almost a little subscript. Big P, R is like a little subscript. And basically what this means is that n is like the total number of things that we have, and R represents how many of those are we actually arranging. So if you have like 4 plants and you want to arrange 3 of them on a windowsill, how many different arrangements of plants could you have? Okay, so this formula for the permutation is given using factorials. Our numerator is n factorial, and our denominator is n minus r factorial. Okay? However, when we use permutations, we can also do this in our calculator. To get to the permutations, we would go to, whoops, sorry. To get to the permutations, we would go to the Math button. Again, you would go to PRB, and then this time you're going to use number 2. and number 2 says that NPR. So what number 4 means is that we have 10 items and we want to arrange or order 4 of them. We want to see how many different orders can we get if we take 4 objects out of 10. So in the calculator, what you would do, we don't start here with the NPR. We would start by putting in 10, then we would go to Math PRB 2 to get the NPR, and now we would put 4. And that's how we would evaluate 10P4 in the calculator. And that gives us 5,040. So to evaluate 6P6, I would do 6, Math PRB2, 6, and press enter, 720. So when it asks us to evaluate those, all you have to do is use your calculator. That's it, okay? So let's use this, let's use a permutation in a word problem. It says, in the Olympics, there are 4 men on a team in the men's 800-meter freestyle relay. How many different ways can the men on one team swim the competition? Well, how many total swimmers do they have on this team? They have 4 swimmers on the team. Now, how many of them are going to be swimming in the race? Well, it looks like it's a relay, and so there are 4 people that have to swim. So what we would do is we would just do 4P4. Just for time's sake, we put that in the calculator, guys, and just trust me, we would get 24. On your homework for these problems, I would want to see both your permutation setup and your final answer. So not just the final answer, but that setup is beautiful. If this helps you, you may do that also. Let's look at example 4. It says 8 teams are competing in the final round of synchronized swimming. How many different ways can the teams finish the competition? Well, we have a total of 8 teams, and we're looking for the teams that finish. So unless something goes wrong, how many teams are going to finish? Probably all 8. And so we want to say we have 8 teams, and we want to figure out in how many ways can 8 of them finish. Can we arrange those 8? And we end up with 40,320. However, all 8 can finish, but only 3 can win medals. So how many different ways can 3 of the synchronized swimming teams win the medals gold, silver, and bronze? Well, we only have 3 medals, but how many teams are there total? There are 8. And how many of these teams can win a medal? Only 3. So this time we have 8 teams, and we want to see how many ways can 3 of them win medals. And if we use 8P3 and evaluate in our calculator as we demonstrated, we get 336. Okay? Last thing says permutations with repetitions. The number of distinguishable permutations of n objects, where one object is repeated s sub 1 times, another is repeated s sub 2 times, and so on, is given by this. N factorial, so that's really the total. And this s sub 1 factorial times s sub 2 factorial times all the way up to s sub k factorial. You guys, this is really just talking about the repeats. Okay? So like if you have the word Bob, for example, like if you switch these 2 B's, that doesn't make a difference, right? But a distinguishable permutation, you would see something different. That's what they're trying to do. They're trying to divide out the repeats so that when you switch the order of things, that it'll look differently. So let's find the number of permutations using all of the letters of the following words. So here we have the word Spartans. And we're going to see how many different ways, if we rearrange these letters, how many distinguishable permutations or distinguishable orders could we come up with? So how many total letters do we have? It looks like we have 8 total letters. Now I want us to look at how many repeats we have. How many letters are repeated? Notice that we have S that's repeated twice. Any other letters? We have A that's repeated twice. So what this means as far as our setup, our total would be 8 factorial. And in our denominator, we had S repeated twice, so we would divide by 2 factorial. And we had A that was repeated twice, 2 factorial. Now before you jump and put this in your calculator, we want to divide 8 factorial by like everything under here, which means that you should put this in parentheses. So if you need to go back up here and put this in parentheses up here, then do that. But you need to put that denominator in parentheses, okay? So if we took 8 factorial and divided it by the quantity 2 factorial times 2 factorial, we would get, we would get 10,080. So 10,080 different, distinguishable, or different looking ways to arrange that word. Let's do the same with mathematician. If you count those letters, you guys, trust me, there's a total of 13 letters. Let's look at the repeats. We have M that repeats twice. A repeats 3 times. T repeats twice. And I repeats twice. So when we're setting this up, we would do 13 factorial over. In our denominator, we have 2 factorial times 3 factorial times 2 factorial times 2 factorial. And again, if we put that in our calculator, we end up with 129,729,600 possibilities. Okay? I'm going to write down the answers to these U-tries. I think it's a good plan to try to get to them. There's work for these U-tries that are down here on ePark too. But those are the answers that we should get for those U-tries. Okay? So you guys can now work on the assignment. Again, if you missed anything, the notes are on ePark too. And good luck. All right, I'll see you guys tomorrow. Thank you.